This is part 2 of the module on PCA used for regression, and in the first part we looked at the OLS, ordinary squared regression, and we understood what sort of line fit it would produce and what exactly we're minimizing, and we said there is another regression line we could build where we would be minimizing the distances to the line itself, not along, let's say, y or x axis like in ordinary least square regression. And we said we do that when x and y variable are not in independent relationship, but they're entering the regression equally. And we said that this orthogonal regression can be useful, or it seems like it may work in a case of this problem. We found in internet, right? Someone was asking about paraglider moving and recording paragliders latitude and longitude, and when Excel was used with OLS to fit the best fit line, the best fit line was not producing a reasonable fit. Right, so we stopped at discussing the nature of the problem, right? So we have this paraglider, and it's or he or she, whoever, the paraglider is basically making spiral type of movements, right? So the paraglider is moving in this thermal, this atmospheric phenomenon, and the wind is, you see, moving this paraglider to north, I suppose, like it's probably moving from south to north. And if you are wondering, you can actually reproduce this map. I will show you how. Right in the question itself, here in the question there is a link. You can try that link, and if you follow that link to stat exchange, you will find the data. So that's what I did. If you pull the data and map it on, let's say, on Google Maps, you will see that it's somewhere in UK, right? This is happening. Okay. Let's see. Okay, so the paraglider's moves are spirals, we said, and we said that there's underlying sort of complex movement which generates these latitude and longitude. And we said, well, maybe if we try orthogonal regression, maybe we will get a better result than normal regression, that OLS, right, the usual regression. So orthogonal regression or PCA for regression, which I called in this case, it has many different names. I listed some of them, like type 2 regression, major axis regression, and so on. And I brought a couple of standard references from the field of ecology. These two books, Numerical Ecology and Biometry. There's also an R package which does it. But as I said in the beginning, it's quite simple. All you need to do is to get the first principal component. So you plug x and y into PCA, get the first principal component. If you draw it, that's your regression. You can obtain the slope and parameters of this major axis regression from OLS regression. There's a way to do it. You can study it in the given references. I just find it easier to run PCA in this case, right? So why is it working here? Well, like I said, we have this paraglider who is a complex movement which generates latitude and longitude, and that's why latitude and longitude are not in independent relationship. They are in a way both dependents of some other factors. So in this case we have this wind which is moving the center of that imaginary circle around which a paraglider is gliding. All right, and there's some other parameters, and if you like we saw, the data looks like this, right? So which makes us think that most of the action is going on along some movement south to north. And most of the variation of the data is along south to north. And that's why if you run PCA on latitude and longitude straight, then you are going to get the PC1, which is directed from south to north, maybe a little bit tilted with the wind direction. And the remaining variation is along the what is it, along the latitude. So most of the motion happens along the latitude and a little bit of it around longitude. So you're going to see the first principal component is going to be pointing up, and then second principal component is orthogonal, so it's perpendicular to it. Right, so we can obtain the PCA regression parameters through the equations which I gave you here, and we're going to look at Excel in a minute and see how exactly it's been done. But this plot is actually orthogonal regression or major axis regression, which was plugged into latitude and longitude dataset, which this person posted with a question, right? So it has a very good fit, I think, and it looks common sense, right? Like as the original poster set of this example problem, we're looking at that hand-drawn common sense best fit line, right? It's almost vertical, showing where the wind is blowing. So we, using this orthogonal regression, we were able to reproduce that line. So orthogonal regression or major axis regression has a few other variants, and in particular, it seems in ecology they like this thing, so they have different names for it. So, for instance, they have standardized MA regression, and that's basically major axis regression, where instead of the covariance you are using correlation, for instance. And that's SMA. There's something they call RMA, which is range major axis regression, and so on. And in ecology they came up with a few rules, and we'll talk about them just in a second, before we after we look at the Excel example. Right, so how did I obtain this major axis regression? And that's a red line in the plot you are seeing here. So I got the data from the poster. The original poster, right, posted the data. It's in an Excel CSV file with 123 observations at, I'm assuming, equal times. And I don't know what's the sampling frequency. Is it every second or every couple of minutes? I don't know that. And that's not that important at this moment. So what I did was I took latitude and longitude, and first in the scatter plot I'm just drawing them straight, right? So longitude along x and latitude vertical axis. Next, what we do is we calculate the covariance matrix here. Very easy, right? You get variance and you get covariance, and then you get variance of the second variable, which was latitude. Once you got the covariance matrix, now we can run a PCA, straight PCA, and in Excel I'm using this function called eigenjk. In the module on PCA, you have a reference to this function, but all it does, it basically calculates me the principal component vectors here, and then it calculates explained variance, and I'm not that interested in explained variance. I'm interested in the first principal component, which is in, let me increase it, right? Let's increase it a little bit. It's in column N, cells N14 and 15. Very easy. We can we get this vector, and then having this vector, I can knowing the coefficients, it's very easy for me to come up with a line of the best fit. How do I do it? Well, I get the min and max of the latitude, and you see latitude is on y-axis. I get min and max, and then I'll just calculate the longitude which corresponds to it according to principal component analysis, first vector, right? So it's actually a very simple formula, right? We know that when we calculate the covariance, the PCA runs on the centered or called demeaned. Means are removed, right? So you add them back. So in this formula, all I'm doing is I'm getting the maximum or minimum latitude, subtracting the mean from it, mean latitude, and then I'm dividing by what? I'm dividing by principal component coefficients for a longitude, and then I'm multiplying it by principal component coefficient for a latitude, right? And I'm adding the mean or average of the longitude. That's my regression line, and you see the coefficients are 10.4, while the ordinary least square regression was wait a second, was a much smaller coefficient. It's 0.28. Right, so the Excel's OLS function was producing something not so reasonable, while PCA is producing a very good fit, right? So it seems we solved the problem, right? Why don't we talk about the details? Okay, well, PCA for regression or total least squares or orthogonal regression seem to work in this case. Now, in ecology field, the practitioners, they came up with a bunch of rules when to use all kinds of these types of major axis regression, like I said, orthogonal regression. I pulled these rules from biometry book to which I referred to earlier. These rules could be interesting, and I encourage you to read them, but it's interesting that sometimes, or quite often in the field of ecology at least, they suggest that you apply the major axis regression in cases where you think that or where you know that your x variables regressors are random. So if you think about the case of experimental physics, let's say, or experimental sciences, natural science, engineering, oftentimes people can do experiments. They can control the x-axis variables. While in finance and economics, that's usually not the case. In most of the time, yes, we can measure it pretty well, but you cannot control, you cannot set Dow index or S&P 500 at level. You just observe it, and in those cases, we will say that X or regressors in observational studies, they are random regressors. Right? We can measure them, but we cannot control them. So a lot of our studies and a lot of regressions in finance and economics would be on random regressors, but we barely ever use this type 2 regression, the orthogonal regression. So that's why I wouldn't say that every time you have a random regressor you should be using orthogonal regression. I don't think that's the case. I think, to me, the main criterion when to use orthogonal regression is precisely what I just said, or what I've said several times, that the variables should be on equal terms to each other, right? So like in this case, longitude and latitude, it's not like one of them is defining the other. They are defined by the complex movement of the paraglider in this particular problem. So that was part 2.